In this next section of Chapter 10, we'll be looking at enthalpy, using enthalpy with stoichiometry problems, and also doing Hess's Law, which looks at changes in enthalpy. So to look at this, the first thing we want to touch on is the idea of endothermic and exothermic reactions and how those are written with regards to enthalpy changes. Enthalpy, by definition, is the energy content of the reactants or the product. So we generally look at the change in enthalpy, which is the difference between the energy of the products and the reactants. So products minus reactants. That's where you get your delta H values. Remember, an exothermic reaction is giving off energy. So one of the ways that you might see this written, let's say we have a combustion reaction. CH4 plus O2 forms CO2 plus H2O. In that case, what you might see is we first balance this equation. We need to put 2 here. That balances out the hydrogens, and then 4 oxygens, so let's do here. One way you might see this written is with an energy term, where the energy is listed as part of the reactants or products. In this case, since it is exothermic, the energy would be given, say here, 520 kilojoules. Now, that's the number I came up with. It may not be the exact number for this equation, but get the point that in an exothermic reaction, the energy would be a product of the reaction. In an endothermic reaction, we would see the opposite case. You would see the reaction written. Let's say, for example, we had the reaction N2H4 plus H2 forms 2NH3. In this case, it's an endothermic reaction. We would put the energy as a reactant. So if you see energy on the reactant side of the product of the equation, you know it's endothermic. If you see energy on the product side, you know it's exothermic. There's another way of doing this with delta H. The other way would see the delta H value listed instead of writing energy as a reactant or product. In this case, we'll write delta H, change in enthalpy, and give it, it'll be positive for an exothermic reaction, so positive 520 kilojoules. So by seeing the delta H and knowing it's a positive value, you know you had an exothermic reaction. In this case, N2H4 plus H2 forms 2NH3. You would see your delta H value as a negative. This would tell us that it is endothermic. So if you see negative delta H values, you know you have an endothermic reaction. Positive delta H values, you know you have an exothermic reaction. Now we can use these in stoichiometry problems. So here's an example of a typical problem. How much heat is absorbed? So we know it's a, when 38.2 grams of bromine reacts with excess hydrogen, according to the following equation. So we're going to start with our given value, 38.2 grams, and remember bromine is a diatomic, so Br2. First thing we need to do is convert that to moles. 1 mole bromine for every 159.80 grams. We get this from the molar masses on the periodic table. So 159.80 grams. Once we have moles, now we can use this delta H, because delta H is actually given generally in kilojoules per mole. And it's based on the reaction. So we use the coefficients of any of the reactants or products when determining this. So in this case, the energy is 72.80 kilojoules. And we have, in this case, 1 mole, and we're going to use bromine, because that's what we solved for earlier. Since the coefficient of bromine is 1, that's where we get this 1. If we'd been doing HBr instead of bromine, we would have used 2 moles in the bottom half where this 1 was when solving the problem. To solve this, go ahead and multiply and divide. We get 17.4 kilojoules. So this is a typical stoichiometry. We can use kilojoules per mole as another conversion factor here in this part just like we've used other conversion factors in stoichiometry. The other big thing that comes out of this section is Hess's law. Hess's law says that a reaction can be written as a sequence of steps or sequence of step reactions. The total change in energy of the reaction is the sum of the change of energy of each step. So if we have multiple steps that can make up a reaction, if we can add up the delta H for each reaction, we'd have the delta H for the overall. These typical problems work kind of like a puzzle. You'd have multiple reactions given, in this case 3 reactions. I'll label this one number 1, this one number 2, and this one number 3. We're trying to make this top reaction. N2H4 plus C4H4O forms CH2O plus N2 plus 3H2. We have to figure out how to put these 3 reactions, 1, 2, and 3, together in a way that gives us that top reaction. The general easiest way I have found students to be most successful with this is to start with each of your reactants and products, find those reactants and products that are only in one equation, and figure out how to put the equation correctly to get the reactant or product on the right side with the correct coefficient. So our first reactant here is N2H4. N2H4 is only found in reaction number 1. So I'm going to use reaction number 1, but what I need to do here is reaction number 1 has N2H4 as a product, and I need N2H4 to be a reactant. So I'm going to flip the reaction. Put the products on the reactant side and the reactants on the product side. So N2H4 becomes a reactant. H2 is my other reactant. Those were the 2 products. And now my reactants become my products. So 2NH3 becomes my product. This gives me N2H4, which I was looking for in the original equation that I'm trying to solve for. You must do the same thing to the delta H that you did to the reaction. So if I flipped delta H, I need to flip the reaction, I need to flip delta H. So I get negative 22.5 instead of positive 22.5. The next thing I have is CH4O as a reactant. I find CH4O in number 3. Once again, I want to flip this. CH4O reacts to form CH2O plus H2. This is also flipped, so this also becomes negative 81.2 kilojoules. That gives me the second reactant. Now, looking at the products, the product CH2O is already a product from reaction number 3, so I have that. N2, I need N2 and 3H2. Well, N2 and 3H2 are in reaction number 2, just as they are written. So I'm going to leave that reaction just like it's written. 2NH3 forms N2 plus 3H2. So I'm going to leave the delta H just like it was. The one thing that you are not seeing in this example problem is I do not have to multiply the reaction by any number to change the coefficients. The coefficients actually work out just fine without doing any multiplication. But if you needed, say, the coefficient of N2H4 to be 2, I could multiply the whole first reaction by 2, which would mean I'd also need to multiply the delta H by 2. You can also multiply by fractions if you need to. Once you've done all this and you think you have the right answer, check to make sure you've done it right by adding together all the reactants. N2H4 plus H2 plus CH4O plus 2NH3. So I've added all the things that are on the reactant side of the 3 reactions. Now I'm going to add all the things that are on the product side. 2NH3 plus CH2O plus H2 plus N2 plus 3H2. Now, go through this reaction and see if anything cancels on both sides. For example, 2NH3. 2NH3 is the same on both the products and reactants, so I can cancel that out. H2, I have one H2, It's 1H2, so I can cancel one of those out. Those are the only things to cancel, so I'll write the remaining things. N2H4 plus CH4O reacts to form CH2O plus N2 plus 3H2. Now, check that, make sure that's the same reaction as we were trying to solve for, and indeed it is. So now we need to solve for delta H. To get delta H, all we need to do, I'm going to do this up here where I have more room. Delta H is now the sum of the three delta H's. So negative 22.5 plus negative 81.2 plus 57.5. Add those three together and you'll have the delta H for the overall reaction, which is negative 46.2 kilojoules. And that would be your answer to the problem. We'll do more examples of this in class over the next couple of days, and you will have lots of chance to practice with this. It's something that's going to take a little bit of practice to get used to the flipping, the multiplying it by numbers and fractions to change the coefficients, trying to get that right final reaction.